All right, it's time. Welcome to my live stream about the formation of the solar system. It's what I'm going to talk about for an hour in this session. I'm not just the webcam a little bit so the light falls outside. Yeah. Okay. Yeah, I am Marcel-Jan Krijgsman. And I am from the work group Moon and Planets of the Royal Netherlands Association for Meteorology and Astronomy, or de Koninklijke Nederlandse Vereniging voor Weer- en Sterrenkunde, the KNVWS in the Netherlands. And what I do is I write on Facebook and I blog about things that happen in the solar system, new missions to the asteroids, comets, and all that kind of to planets, plans to land on the moon. But I write about that in Dutch because the audience, the target audience, is Dutch. And I started doing this something like 6-7 years ago to find more members, because the members of our group was aging basically, so I tried to find new members. If you want to find anything I do in English, you probably could go to my Twitter account. There I write things. There my target language is mainly English. All right. Okay, so this story is about the formation of the solar system, and it's a topic I'm very interested in, because actually long ago, when I started to get interested in spaceflight, I got books for my birthday when I was young, and they told, oh, we're doing these wonderful missions to the planets, and the question sometimes was, why are we doing these missions to the planets? And the answer was to find out how the solar system was formed, where we come from, where our planet comes from. And even even now you can find this. For example, I found this somewhere in an article, I think from Nature Astronomy, where they said, well, we do this this mission to an asteroid or to a comet because we want to find clues about how the solar system was formed. And I heard it for such a long time, and I realized when I read some article about the findings on Rosetta that actually we have found a lot of these clues, and I want to talk about the pieces of the puzzle that we have found, because I think that's rather interesting. So when we started with sending missions to the planets, at first it was more or less it was more about showing who was first, the space race, but soon enough scientists, astronomers managed to get they not just sent these missions without scientific instruments, but more and more these became science driven, fortunately. But the first missions were all sent to planets, Venus, Mars, and of course the Moon. Even 2 years after Sputnik, the first, you had Luna 2 that impacted the Moon, and that was clearly something about the whole as prestige part. But but we're starting to learn things about these objects that we were visiting, and but what we've learned from the first decades of spaceflight was actually that if we want to know more about how the solar system formed, maybe we should not go to these large objects. And what you see in the last few decades is that scientists, astronomers are getting more and more interested in these small objects. And why? Because these small objects haven't been altered. The original material from where they were built from hasn't been changed much because they don't have a lot of gravity. So they didn't compress this material. There isn't an iron core that has been melted deep inside the object. The original material is often still there, or only slightly changed. I forget to start to save my broadcast, so I should do that. If you have any questions, by the way, ask them in the chat. If I'm getting way over your head, maybe it's me. So ask a question and I will try to answer it. And hopefully the session still fits in an hour. So what you see is that we see Rosetta go to a comet, 67P Churyumov-Gerasimenko. You see Hayabusa, Japan, sent not just one but two missions to an asteroid. NASA sent OSIRIS-REx to an asteroid. We see New Horizons fly past, not just Pluto, but also Aracot, it's now called, or 2014 MU69, a small object in the Kuiper belt, and we learn that from that. And also we learn from meteorites still. Even though these are altered when they had to go through the atmosphere with a lot of heat and everything, we can learn stuff from these as well. So the small objects count. About this promise, before Rosetta arrived at the comet, the European Space Agency had a wonderful short movie called Ambition, a science fiction movie where two people talk about, in the far future, how we at one point learned where we came from the Rosetta mission. And that was very nice. But later I read about what they found on Rosetta, the findings, and they actually showed from the results you could learn that actually we did learn a couple of things about how the solar system formed, but there never was a movie about that. So that's why I'm doing this session. By the way, look it up, ESA Ambition. It's a nice movie. So I have the habit in my talks about astronomy to go a little bit into the past to see how we thought about things a while back. So the idea is that the solar system formed from a nebula of dust and gas. And I always thought that this was something we came up with during the space era, but it turns out it actually this theory actually existed much earlier. I learned this from a book. By the way, my webcam image is always on top of something in my picture, in both my presentation. I have it here. This is a popular science book from 1905, written in Dutch, translated from German, I think. It's actually a lot of fun when you read it. This is how people thought about science, about astronomy, how about the planets formed 115 years ago. When you read it, you see that, for example, how do you explain a supernova when you don't know nuclear physics? That's interesting. They assume that stars just smash into each other. That is how these enormous energies are produced. A lot of other stuff are interesting to read, but it's also you also read something about how the solar system was formed, and they also talk about a nebula, a dust cloud around a star that just has been created, the sun. So apparently this theory existed much longer, and when I started looking into it, I found out that actually this theory already started in the 18th century. It was Immanuel Kant who came up with this idea, basically, although he and here we go again. I'm in front of Emanuel Swedenborg. Yeah, it's hard to get out of his way. Yeah, so actually Emanuel Swedenborg, I think he was a Swede because it says so in his name. He already came up with a theory that the solar system was built from dust around the fresh new star that is the sun in 1734, and Immanuel Kant started looking up and started combine the idea with the nebula you can see in the sky with a telescope, and he combined that idea from, hey, there are nebula in the sky, maybe we came from nebula. Even though that sounds maybe logical, in that idea in a time where mainly the idea was that God created the planets just like that, that was pretty revolutionary back then. Yeah. Oh, by the way, Immanuel Kant, he's a philosopher. I only knew him from the Monty Python song by the Bruces. So all I knew about Immanuel Kant was that he was a real person, but apparently he really did some scientific work as well. And when you look with a telescope at these nebula, what we now know from the Hubble Space Telescope, yes, there are actually these nebulas, and actually stars are formed in there. And you can even see this better with the Hubble Space, the later edition on the Hubble Space Telescope, the Wide Field Planetary Camera 3, which can also view things in infrared and ultraviolet. But infrared is interesting. It has the neat trick that you can look through the dust. I see that my broadcast is not saved. Okay, I have to do it later on. You can with an instrument like the Hubble, you can look through the dust and see the stars actually being formed in there. Another interesting thing that you can do with Hubble is because Hubble is now 30 years old, you can see when you do multiple pictures over time, you can actually see stuff happening in that dust cloud. You can see jets of material being thrown out at the newborn stars. So you can actually see this moving over time, over the years. So turns out, so Immanuel Kant, well, he was pretty much right about these dust and gas clouds from which a star formed, and so on. But there were some problems with this theory, and the problems were that when you started calculating if this could happen, you would apply math to it, you would find out that things would not coalesce to larger objects like you would think they would do. And actually this is where the mathematicians stepped in, and one famous mathematician is Pierre-Simon Laplace. For me, also very famous for the bad grades I got when I had to learn integrals. The Laplace transformations he came up with. So he was a pretty smart guy, or I'm pretty dumb. That could also be the case. And but he started doing calculations on how these dust clouds could coalesce to planets, stars, and planets. And this, mind you, is long before he could say, "Let me run that through a supercomputer." But he came up with the idea that there was more than just gravity and a lot of stuff. You also needed heat. He came up with the idea that the sun originally was probably had a hot atmosphere where that affected the stuff in that dust cloud. And nowadays we can see these dust clouds around young stars. These are 20 stars, young stars, and the dust clouds that orbit around them. So this is pretty amazing. ALMA, the Atacama Large Millimeter Array, the combination of multiple submillimeter telescopes in the Atacama Desert in Chile. They give us these amazing views on other stars, and you can see the dust clouds around the stars, but you can also see that there are some empty lanes. Apparently something is being created in there, protoplanets that we cannot yet see. So that's pretty cool, and it's just not happening in one place. You can see several of these young disks, young stars with these disks that have these lanes in them. So this theory still also had some problems. I won't go in detail what these problems were, but actually there was one guy, and this is the case with many. Often when I talk about the history of things that we learned, the astronomers that came up with ideas in the 20th century, these astronomers are often forgotten. So this is a guy called, the Soviet astronomer called Viktor Safronov, and he came up in 1969 with a theory about how this could all work better. And this uses the idea of runaway accretion. So runaway stuff that is coming together, clumping together to at first planetesimals, very small objects, a couple of meters, I think. And then these planetesimals bump into each other and crash into each other, and later become protoplanets. And from there we get the actual planets. And that he was right about this. By the way, it was important enough that NASA decided to create a translation in English. So that is where you can see the right picture. We can actually see this happening. The Hayabusa 2 mission, Japan's mission to the asteroid Ryugu, found out, and this was recently published, that the material that this asteroid Ryugu was built from was the remnants of a collision that happened between and that the original material was from planetesimals. So this is one of these planetesimals that Safronov predicted that would have existed in the first at the start, and it actually crashed, like the theory says. And later on, this rubble started to come together again, and then we got the asteroid called Ryugu, which is I think something like 900 meters in diameter. So it's not that big. It almost has no gravity, but it came together over time. So another thing you might ask is, so okay, we have suddenly we have dust and gas, and then suddenly there's enough gravity. Some parts clump together enough that there's enough gravity that a star comes into being, and these other the rest orbits around that star. And then, but what was before all that? Well, the idea is that this dust and gas is from these are remnants from supernovas before our sun started to exist. But you might wonder, is there anything left of that? And it turns out not exactly, because our sun blew it away in its early stages. But yet we seem to find sometimes some material from the time, but it's very rare. One example is a stone called the Hypatia stone they found in a Libyan desert. It's called a glass desert, and it's a glass desert because there was an impact, meteorite impact in that desert. So the sand became glass, and in that glass they found this object, this stone, which has a completely different composition of than other meteorites we usually find. So this Hypatia stone, they're still investigating it. And when I wrote about this in the blog 3 years ago, I said we're probably going to hear a lot of it, but actually I haven't heard anything about it since. So I'm not sure if they found anything new. But what they found in the stone was not just a different composition that they were accustomed to, but there were also there was interstellar material. These polyaromatic carbons they found in there, and these are interstellar dust basically. And they found all kinds of other stuff like metallic aluminium, something you rarely see in the solar system in the wild. So while we do not know, while I haven't heard much about this stone anymore, there recently was another article where they said they went looking for pre-solar grains in a meteorite. This is another way to find materials from before our solar system. These grains were found in the Murchison meteorite, and this meteorite was found in Australia near a place called Murchison. What they did, they removed the original, they cut a little piece of that meteorite and removed the meteorite material until they found some grains in there. And these are pre-solar grains. So what they did, they wanted to know the age of these, and they have based the age on the amount of solar cosmic rays that have bombarded them. And the interesting thing is, so they looked at the neon isotope, and actually they learned recently from Voyager 1 how much cosmic radiation you can expect outside the heliosphere, outside the influence of the sun. And from this they could calculate how old these materials were. And the age of the oldest pre-solar grain that they found was 7 billion years old. So our solar system is 5.56 billion years old. So this is pretty old. Other particles were a little bit less old, but still older than our solar system, 5.5 billion years old and 4.9 billion years old. So it's pretty interesting how they managed to find that out. Okay, so we have this dust cloud of dust and gas. And how do you get... Mr. Safronov told us there's a theory that you get from dust to planetesimals. But how do you get from these just dust and gas circling around the sun to a little bit bigger objects? Actually, there were multiple theories about that. And it was only until the Rosetta mission that they found the solution. So what they did, you remember the Philae lander that landed on the Comet in 2015, I think, or no, 2014, maybe the end of 2014. Anyway, around that time, what they did, they transmitted radio signals through the comets between Philae and Rosetta. I'm not exactly sure which one had the transmitter, probably Rosetta. And they looked how the comet looked from the inside, and what they found out was that the comet is very porous. It's actually it's built from the original material, but it's like 70% nothing and 30% material. And they say that this is because it was built from so-called dust pebbles. That's basically from Rosetta. They learned that the material that the comets were built from and the other stuff in the solar system is built from is from tiny pebbles of dust about the size of my thumb. So really pebble sized. And this is not hard as a pebble that you find on the beach or something, but it's near a river or a lake. It's like Rosetta found nearly very little material, very light, very a lot of nothing in it basically. But what you see is after they found this there was a paper about this that came out in 2017. You can see that the later papers that scientists wrote, astronomers wrote about this, how planets formed, they all use this theory. So this is all you ever see. After this, you see theories, scientific articles about formation of planets. They all use the dust pebbles. Here's an image from a scientific paper I found later, and what you see here is that the dust pebble. These pebbles, these are formed, and then some of them come together. They become planetesimals, and some of them come even. They get even a little bigger. They become protoplanets, and these protoplanets get kind of a very faint atmosphere around them. Of a little bit, there's a little bit gas, but it's enough to slow down other dust pebbles, and that's why the other dust pebbles suddenly are attracted by the very little. They're slowed down by the atmosphere, and they attracted by the very little gravity that there is, and that is how planets can quickly grow in the beginning of the solar system. Now you can imagine that material that would be very interesting to investigate in a lab. So NASA has actually been thinking about getting this material. This was the idea for there's a mission that they came up with. It's called Caesar, and unfortunately it was not selected. It had to run for a slot in the New Frontiers for the New Frontiers budget last year, and they had to run against the very cool Dragonfly double quadcopter drone that will go to Titan, Saturn Moon Titan, which is, I had a hard time, if I had to choose, I would have a hard time. Having a drone on Titan is so pretty cool, but having this material, the pristine material from the solar system, it's also pretty cool. So I would have a hard time to choose, but they chose the quadcopter, which I think will have wonderful pictures in 2036. Yeah, we have to wait a bit before it arrives. Anyway, so it looks like that this is not going on, but curiously enough, I recently found an image on the Twitter account from JAXA, the Japanese space agency, where they said they are working on they're contributing on this mission. So is it still going on? Is it still chance? I don't know. Now, this idea about these dust pebbles, this is actually interesting. It's not just interesting on an astronomical level. It's interesting in the rest of in other scientific fields as well. There was a wonderful video about scientists who calculated how these would be formed, and they said this is not just this could not just apply to dust pebbles, but also it could tell something about other particle flows through a gas, like how raindrops form in a cloud, how volcanic ash becomes reacts in a plume, and that kind of stuff. So that's pretty cool. So we're learning interesting stuff from that, and we actually learned more from a next experiment. This is something that came out last year. Scientists wanted to know whether this formation of these dust pebbles would go faster if you had a little bit electricity, a little current running through them. So this experiment actually did not launch into space. They used a drop tower in Bremen, the German city. They have a tower of 146 meters tall, so that is 450 feet or something. Anyway, a tall tower, and you can put an experiment in the top, and you can drop it, and it will be will experience microgravity for 9.3 seconds, and then it will fall in a lot of styrofoam ball pit or something, and then you can maybe rerun your experiment. It will not be destroyed by the fall. So they done this, and they tried the experiment without an electrical current, and they tried it with an electrical current, and probably different variations of that. And they found out with electricity it runs better. And this also has applications outside astronomy, because they said you can use this theory, these findings, if you want to create new prescription drugs in so-called fluid bed reactors. So you can create these medicines, these prescription drugs, quicker when you apply a little bit of electricity when you create them. So that's pretty cool. So we're learning a lot of interesting stuff here, and it's not all about the formation of the solar system. Okay, so we have this disk of dust and gas, but there's something else you need to know. There is heat, like Laplace said, but it's not evenly distributed. The sun is very hot in the beginning, and within a certain line, it's so hot that when you have water initially in that cloud, but it is evaporated and moving outside to the further beyond a certain line. This is called the snow line. And you can see this, how planets and moons are formed, what they are made of. Close to the sun, you can see you have planets made of metal and rock. Take, for example, Earth. Earth has an iron core and it has a lot of rock around it. But Mercury, for example, also we recently learned has an iron core, and that's why it has a weird magnetic field and all that kind of stuff. But when you look at, for example, the moons of Jupiter, there are a lot of them are built from ice. Take Europa, Ganymede, Callisto. So this was because these were formed beyond the snow line. So this where water ice could still exist. And when you go even further to the Kuiper belt, there you can also find ices like nitrogen. Take, for example, Pluto. There you have, the heart of Pluto, Sputnik Planitia. Well, this has nitrogen ice, and other places on Pluto have methane ice. And you also find other Kuiper belt objects with carbon dioxide ice and that kind of stuff. So has to do with the heat of the sun when the solar system was formed. So yeah, like I said, when you look inside the planets, for example, Mars also has an iron core, and we're learning more about that from the InSight mission. And the Moon has some kind of iron core deep inside, and yeah. Oh, this was a recent development. A couple of years, 1 or 2 years ago, they found out that Mercury, from the Messenger mission, also has an inner core with a molten iron core outside the inner core, and rock around it. So this is how our rocky planets seem to have formed. But that leaves the question, how on earth then did we get oceans? Where did that water come from? And that is actually a question that we're still asking ourselves. This is an unsolved problem. And it's not just that our planet has oceans. but it seems more and more like Venus once had oceans, and Mars, we're pretty sure that Mars had a lot of water. So where did this water come from? Well, this is what the Rosetta mission was set out to find out. What they did, this is the nice animation they made for every people, so that people could easily understand what it was doing. So in that animation, Rosetta was lurking from a cup of Earth water, and then from the water from the comet, and it tried to find out if it was the same. What Rosetta actually did, it was looking at the ratio between hydrogen and the heavier isotope deuterium, and that ratio tells you something about where the water came from. So Rosetta could have found that, oh yes, water is from comets, but it turns out it wasn't true. So we thought that it was like that, but we were disproven. And now we're starting to think that it's probably from asteroids. And whether that is true, we will find out pretty soon, because OSIRIS-REx is collecting samples from Bennu, and Bennu is an asteroid that has water in its rocks, and OSIRIS-REx will bring that material back to Earth in 2023. Also, Hayabusa 2, the Japanese mission, will bring samples from Ryugu to Earth in the end of this year, actually in December. But this was we found out that it was a dry comet, so maybe we're not learn that much about that yet. So we have to have a little bit patience. Another thing I was thinking I probably have to explain is some talk. I said the solar system is 4.56 billion years old. How do we know that? Well, we learn a lot from meteorites in that regard. A couple of especially carbonaceous chondrite meteorites. They have these lighter colored inclusions. They are called calcium and aluminium rich inclusions. And these are actually the materials from the very beginning of the solar system that we can find here on Earth, because it fell to us. It was delivered to us. And what they do is they actually look at isotopes. So you might know that atoms have a half-life. Well, some atoms have a very, 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 very long half-life, like uranium-238. It has a half-life of 4.5 billion years. And another isotope has a shorter half-life. And what you can see when you look at the isotopes in these inclusions is that after all the billions of years, you're left up with a lot of, for example, lead isotopes. And from the ratios of these lead isotopes, you can actually learn what the original material was. That's the best that I can explain. And you can look at these different isotopes, and you can create a graph, and you can actually calculate how old the original material was. And from this we learned that the solar system is 4.55 or 4.56 billion years old. Some even are more specific, 4.563 billion years old or something. I read somewhere. So we're pretty good at calculating this age. And of course we will calculate the age of materials that will be brought back by the Hayabusa mission as well. And this is the material that is not gone through the heat of the atmosphere. Well, it will have been gone through the heat of the atmosphere, but nicely delivered in a return capsule with a heat shield, and it will not be altered as much as meteorites, or hopefully actually not altered at all. So this is how Hayabusa 2 took a sample from the comet Ryugu. It has a sample horn, and it is put on the asteroid. But what you don't see is that it shot a bullet in the comet, and then all the material shot up. That is why it's reacting so violently. Not just because the asteroid has almost no gravity, but it the bullet create a whole hullabaloo there. So we're still very much at the beginning of the solar system. When can we see the first planets? Well, actually pretty quickly. Jupiter is formed, as far as we now know, very, very quickly in 1 million years, which on an astronomical scale is in a blink of an eye. And how do we know that? Well, there are a couple of things. The theory of the dust pebbles help us here. But also we've looked at two populations of meteorites that we found out came from the same region at the very start of the solar system, because we found the same contents in them, but they now come from completely different places, and that is because an early Jupiter has drawn these populations apart. So they were the same material, but now they're at completely different places in the asteroid belt, and yet they have the same starter material basically. That's one of the ways that we know how Jupiter has formed so quickly. So Jupiter was quickly on the scene and started to take a lot of material, and we even seem to know now that Jupiter grew in three stages. First stage, it was growing by these dust pebbles, attracting these dust pebbles, and then other planetesimals were in the vicinity, and they started bumping into each other, and they created secondary planetesimals, and these were picked up by Jupiter. And then it was a planet, I think something like the size of Uranus or something. And in the second stage, Jupiter is really picking up all the materials, all the dust pebbles in the area, so that other planets, protoplanets, cannot form. And it starts to attract a little bit of a atmosphere. And in stage 3, it really guzzles up all the hydrogen and helium in the area. And it really gets a big atmosphere, and it becomes even more powerful. So that's how we think Jupiter has formed, and this is pretty interesting. So, and Juno is helping us to see what's on the inside, so that also helps to form that theory. The Juno mission is a mission by NASA that is orbiting Jupiter at this very moment, and it was very much its target was very much to look at what's inside Jupiter. So, well, that's all nice and good, but where is our planet? When is Earth coming up? Well, actually, it took a little bit longer. We think it started 20 million years after the formation of the solar system, and the idea is it looks something like this. This is the geologic era of the Hadeicum, and we actually have absolutely nothing from that era that you easily can find in the ground, because, well, one of the reasons that we find very little of this is that at 100 million years after the formation of the solar system, this happened. There was another protoplanet called Theia. It was about, well, protoplanet. It was the size of Mars, so it's not that small, and it's kind of bumped into us in Earth, and from this we think the moon was formed. So it was a large impact. This must be pretty catastrophic. There was a lot of this. It was a disk of debris around the young Earth, and from this later the moon coalesced, and we had a very large moon actually compared to for the size of our planet. It's a pretty big moon, and this theory still sort of stands, but there are a lot of ideas. There are a lot of problems with it yet. We're not entirely sure that this is exactly how it happened. One of the problems is when you look at all the samples that Apollo brought to Earth, and Apollo brought hundreds of kilograms or hundreds of pounds, basically, to Earth. But the material is so much like the material on Earth. I don't mean that there's moss growing on it, of course, but I mean the rock, the basic materials of that the rock was made of, is pretty much the same. And that's a problem, because when a protoplanet, different protoplanets bumps into your planet and a moon is formed basically in part from that Theia object, you expect that there will also be parts of Theia in there. There would be components from that. There should be rocks or material from that, and we don't find that. So that's a problem. This was a very violent time in the solar system, and a lot of planets have found, had to deal with the consequences. For example, why is the planet Uranus orbiting on its side, and why is its magnetic field rotating at a completely different angle than the rotational axis of the planet? That's kind of a problem. It probably was hit by something large. Mars has a deep basin where we think the oceans have been in its very young existence. That just didn't create out of nothing. There was some probably a big impact, and it's probably also the reason why it doesn't have a really good magnetic field, or there's very little of it left. Probably like you hit a magnet very hard with a hammer or something, you can disable the magnetic field. Something like that must have happened. Jupiter, this we learned recently from the Juno mission. Like I said, Juno was meant to find out what the core of Jupiter is like. This is interesting in the theory of the formation of the solar system, because Jupiter has so much material. It's the biggest planet, it would be, and we didn't know what was on the inside, so that you don't know a lot about a lot of material in the solar system. So we think now that Jupiter was hit by something like a Uranus-sized object. And from this, the core still, you can see the effects of that accident from long ago in the core, because the core is not a sharp, distinct core, but it's fluffy. So it's not, it's not a nice line. It's not like you could stand on the core of Jupiter because you would be crushed, but there's nothing to stand on, basically. Because it's, like I said, fluffy. Another thing, so why don't we have anything from the old these very beginning of our Earth? Well, plate tectonics is one reason. The material on the Earth is mowed over every time over millions of years. Another thing is life. Alters a lot of material. So you have a very hard time to find anything very old, any old material on the Earth. The oldest material you can find is something like 3 billion years old, which you can find in Greenland and I think Australia. But actually, another good place maybe to look for old material from Earth is the Moon. Apollo 14 brought this rock back to Earth. It's called Big Bertha, and it has these lighter inclusions. And they found out in the lab that these lighter materials were created in a Earth-like oxidized system, as they said in the paper, created at Earth-like temperatures. And it looks like that something hit Earth and thrown up the materials which landed on the Moon, and the Moon was much closer 4 billion years ago, because we think it's 4 billion years ago, 4 billion years old, this material. And then another impact happened on the Moon, and this material was molten, and the Earth-like material was molten in this rock. So that's what we think has happened. We can't prove it yet, but it's very intriguing. And I'd say when we're going to land on the Moon again, astronauts are probably given the task to look for more of this kind of stuff, because it could be very interesting to find actually very old Earth rocks that are basically older than we can find here. what happened after that is that the moon, we know that the moon has so many craters, it looks like that there was still more material falling on planets and moons later in the history of the solar system, and we call this the late heavy bombardment. But actually there was an interesting article a while back when they said, yes, that is so nice, but we based this on samples from Apollo, and these Apollo missions, the thing about these Apollo missions is they all landed pretty close to the equator of the moon, because it was safer, because you could easier go back to the Earth from these places. And that is different when you land on the poles. You need more fuel to go back. So it was a good reason to do investigations like this. But what they say is that all these landing spots that Apollo landed basically had some material that was thrown up when the crater or the basin called Mare Imbrium was formed. So they actually did some investigations because on other samples, because not just Apollo brought materials back from the moon, there were also 3 unmanned Soviet lunar landers that brought very little amount, something like grams instead, hundreds of grams instead of hundreds of kilograms back to Earth. But they landed on some spots that were outside this area where Mare Imbrium material fell. I'm not exactly sure if this actually changed a lot of stuff in astronomy, but this was an interesting thought. So, what happened then? Well, this is something we learned. We're starting to learn actually. People started to think about that maybe the planets were not always fixed on their place that they are now after they formed, and this must have happened somewhere between 1 million and 1 billion years. So that's a pretty wide margin. But we get more and more proof that the planets migrated. And we started to learn this when we've discovered the first Kuiper belt objects. Kuiper belt objects are pretty far, and so they were pretty hard to find with telescopes that we had before the end of the 20th century. But then adaptive optics was made its appearance, and astronomers built larger telescopes because with adaptive optics they could see sharper through our atmosphere, because they could correct for the vibrations in the atmosphere, basically. And what they found, when they found more and more Kuiper belt objects, they found they all had these elliptical orbits. Now, all objects in the solar system basically have some kind of elliptical orbit. They're never very circular, entirely circular. But these objects were clearly, when you looked at the orbits, their orbits, they were clearly not circular. This was something that influenced their orbits, and this got some people thinking. So at first, we also, okay, this is a side step, but we also found out more recently from the Dawn mission, another different space mission from which we got a piece of the puzzle, that Ceres is probably not from the asteroid belt where it's now. We found that Ceres has materials that you are normally find on objects that form in the Kuiper belt objects, like ammonia and that kind of stuff. Little side step there. But let's get back to... So astronomers were thinking, what could have happened? So they came up at first with the Nice model, where they would have the gas giants migrate. And it was a kind of nice idea. But the thing is, this is our solar system, not on scale. So we have Mercury, Venus, Earth, Mars, and we have a couple of asteroids. With asteroids, you see the green and the blue asteroids in the asteroid belt. These are populations of stony types and carbonaceous types we find in asteroid belt and Jupiter. But when they run this ID through a computer simulation, they always got this: Venus, Earth, Mega Mars, and a couple of other little Marses in asteroid belts, and Jupiter. So and this is clearly not the case. So something still was kind of off. And later on, we also started to find our first exoplanets. We found with the Kepler telescope, but also Corot, the French exoplanet space telescope. Before that, we found, and the first exoplanets we found were a lot of hot Jupiters. So that was weird. At first we thought, well, hey, these are big planets circling around suns in a matter of days. So of course you can find these much earlier than the planets that take years to orbit around their star. Of course we find these first. But then we found more and more and more. And it turns out, well, it's not exactly just an aberration. It's not just something that is... we didn't just find some outliers. It actually happens pretty more often than we thought. And so it really looks like that sometimes large gas giants are getting closer and closer to the stars. Excuse me. Until they are so close that they get very hot, the hot Jupiters. So that was also a thing. So we learned that also. And then in 2011, a couple of other astronomers came up with another idea how the solar system formed with migrating planets. And this is called the Grand Tack hypothesis. Now, hypothesis means we kind of think it might have worked like this, but we still have to prove it. Still, it's an intriguing idea. So what they thought was you had the gas giants appearing pretty quickly. That really seems to be the case. And then they moved closer and closer to the sun. Maybe because of resonance in orbits or something. I'm not exactly sure how it worked. I'm not sure the astronomers know how it worked, but okay. But what happened was that Jupiter got very close to the sun at 1.5 astronomical units even. So that is, well, our Earth is at 1 astronomical unit because that's how we define an astronomical unit, how close Earth is to the sun. But Jupiter got pretty close to where we are now. And then later on, the gas giants retreated, became in a different resonance, I think, and later on Jupiter arrived at its spot, and Saturn arrived on its spot where it is now, and later the rocky planet could form. So we have to prove this yet, and we're looking for ways to prove this, but this is the best we can come up with for now, unless there's anything new that I haven't found yet in scientific papers. You can also see other some kind of other. You can see this also at the asteroid belt, and again another reason why asteroids are so interesting, because you have these asteroids. They were probably two distinct populations: stony type asteroids and carbonaceous type asteroids. And the stony type asteroids were close to the sun, within the snow line probably. And then this migration scattered the whole lot. And later on, you find, and when the large planets went back further from the sun, you have an asteroid belt with the different types of asteroids all mixed within, sort of. Still, you can find some stony types a little bit close to the sun, and the carbonaceous a little bit further from the sun, but some are mixed. So there's that. And also, what they think has happened, and I have to get my picture out of the way there. What we also think that has affected the Kuiper belt as well. So you had these Kuiper belt objects formed on their spot, and then the gas giants and Uranus, gas giants basically pushed Uranus and Neptune outside, and Uranus and Neptune pushed the Kuiper belt objects to long elongated orbits. Because when you move a Neptune close to a Pluto, for example, it will affect the the point of orbit of the Kuiper belt object that is furthest from the sun. It will get further, basically. But the closer part will still be about the same space. Yeah, you could try this in a simulator like Universe Sandbox. It's interesting to try. So there's that. And also there's probably the effect of, we think there's also an effect from the hypothetical planet 9 that also affected other orbits of other Kuiper belt objects. So there's also that. So how do we prove this? Well, this is actually, it's pretty hard to do, but it's not. There is a reason why NASA chose to launch the Lucy mission to the Trojan asteroids and the Lagrange points 4 and 5 around Jupiter. So Lagrange points are points where Jupiter, in this case Jupiter and the Sun, are pulling just as hard, and basically there's some kind of stationary spot in front of the orbit of Jupiter and behind the orbit of Jupiter. And the Lucy mission will visit 7 exoplanets. Hi Arctufus and hi Adam all together. Welcome. Yeah, so we think that these objects, basically when Jupiter moved closer to the Sun and moved outside, the materials that it took with it some of these ended up in in these Jupiter Trojans that are still there today. So that's a smart idea from NASA to visit 7 of these asteroids and find out what they're made of. So there's that, and that's the best I can come up with ideas how we are trying to find out if this migration actually worked. Probably astronomers already have other ideas. We're also going to look at other asteroids. Maybe we can learn from that as well. There is the Psyche mission. NASA is going to visit that. It's going to be launched with Falcon Heavy, by the way, I think in 2022. And it will visit a remnant of an exoplanet, a remnant of a protoplanet that from which had a violent collision, and you now can only find the core, the iron nickel core. So that's also an interesting visit. By the way, there are even more missions to asteroids. You also have the DART and Hera missions, and NASA and ESA mission, but that is to prove that you can move an asteroid out of the way so it won't hit Earth. So this is a different purpose. Arctufus says there's also a new theory that planet 9 doesn't actually exist, but planetary debris with the same mass as the theoretical planet 9 can also produce the same effect. Yeah, that's true. But what I read is basically that astronomers try to come up with other ways that these orbits could have, Kuiper belt objects orbits could have been altered, and this was another way that was possible. But you need a lot of debris, actually about the same mass of planet 9. So either there's a planet 9 or there's an enormous amount of debris the size, the mass of planet 9. Yeah, we will have to see what we'll find. I know that Mike Brown, who came up with the hypothesis of planet 9, is still looking pretty much a lot to find out if it's there. So maybe he'll find it. Maybe it's what you call it, red herring or something. It's gonna be interesting either way, basically. Okay. Adam altogether says I'm a planet 9 skeptic. 6K Kuiper belt objects is too few data points. I think they have more data points now, but yeah, I'm not sure. A new large Uranus planet would be cool, but that doesn't mean it's science. I'm just gonna wait and see. That's basically what I'm gonna do. Yeah, so there's that. Yeah, last thing I can say is what do we still want to know? There's so much. Actually, we have a lot of pieces of the puzzle, so that is very cool. So we actually did learn a lot about how the solar system formed. The idea that we actually have an idea that planets were moving, and that that is pretty cool. But there's still a lot of stuff we have to find out. Like I said, did the planets actually migrate, and can we find proof how that? And can we find information on how that happened? That would be interesting. So we're probably going to visit more asteroids. Another idea is what a recent idea that I read was very interesting. Is astronomers still want to have the definitive answer: did the moon form from a collision by an object called Theia? And the one article I read recently, it was published this month, said the one way to find out is to get a sample from Venus back to Earth. So that's okay. That's not, like I said in the article, one does not simply get a sample from Venus back to Earth. It's like that Mortar quote. But what they're thinking is they could launch a mission with a lander, with a rocket on top of it, land, take samples, and then lift the rocket with the samples up on a balloon. And then when they go to the fainter atmosphere, then they can launch the rocket, and it would go back to an orbit around Venus, then dock to an orbiter, and the orbiter would bring the samples back to Earth. And the astronomer said this would be the one thing we need to definitely answer the question. And why is that, by the way? The idea is that basically about the reason, the idea that the rocks from the Earth and rocks from the Moon are so similar, and there's no Theia rocks on the Moon that we find and that we have found until now. That could be because all material is just the same. The Theia is basically built almost from the same material as Earth anyway, and maybe Venus is made from the same material as well. So to answer that, they want to have a sample from Venus, bring it to Earth, and then we can do some measurements in the lab that you cannot do with landers. It is something about I forgot. Yeah, there are certain measurements you can only do in the lab, enough sensitivity to show that yes, Venus has had the same building blocks as Earth and the Moon, and so this could be why the Moon is so the Moon rocks are so Earth-like, basically. So that's one thing they wanted to find out. Yeah, and of course samples from a comet would still be, I think, a lot of astronomers would still be interested in that. So the Caesar mission has not been selected last year, but who knows what's going to happen. So basically these are the large questions that I could find. Probably there are other questions as well, but yeah, we'll see. So that is my story on the formation of the solar system and how far we are. And like I said, when I found out how much we know right now, I was pretty amazed that we are this far in the process, but we're still not finished. But you can see that this is a multi-generational project to find this out. It will take many. It would take a lot of effort, a lot of missions to space, to solar system. Arcatufus, you missed the most of the stream. Well, you can still rewatch it, I think, on Twitch, and I'm going to try to save the Twitch stream to a file on my hard disk, because didn't manage to save the entire stream here on my PC. The saving was stopped at some point for some reason at the start. But when I'm finished, when I get that done, the video will be stored on our YouTube channel, which is called I think Werkgroep Mana Planeten, so it's in Dutch. But I will send the links to the appropriate places, like the Weekly Space Hangout crew Slack, and I sent this invitations to the Skeptic Guides to the Universe Discord and the CosmoQuest Discord channels, and also on Twitter. So yeah, so you can review it later on, and yeah, that's basically all I can say. So I hope you had fun. There was yeah. Of course, Deep Astronomy also had a broadcast. It seems. Okay. I'll send the links later on. I will. It will take maybe a couple of days for me to get to save the stream from Twitch. I have some software that can store that to my hard drive, save to my hard drive, and so it might be in the weekend that I get time for this, because I'm doing this on my own computer because there's other software running there. This is my work computer, but it will be. I will send the links later on. So yeah, with that, I think I'm gonna end the stream. Unless you have any questions, and if not, then I hope you had fun and learned some stuff. Yeah, you're welcome. It's always fun to do this, and I have a lot more presentations, a lot of topics to discuss in future live streams. It's just that my agenda was carpet bombed by my people at my work in the evenings, unfortunately. So it's going to be harder to find a spot that is both when I have time and when it doesn't interfere with CosmoQuest live streams that are already planned. So, but I'll find out. I will find a way. So once again, thank you for watching. I'm gonna finish my cookie and my tea, and I'll see you next time.